spend my time talking to you about Hebrew and Greek. But I have taken the time in my life to learn enough Hebrew so that I can speak intelligently about it when I do. If you are going to talk about ground substance, you better learn about the organic macromolecules before you start talking about it, because those of us who are in the real world, who are trying to convince people in the public education system that the Darwinian model of life is failing. And if we're trying to do that using the science, and we're constantly getting battered and abused by people who accuse us of being Bible thumpers when I haven't said anything about religion whatsoever, you're making life more difficult. So learn the science or don't talk about it. That would be my suggestion. Y'all can pass that along to your religion friends after I show it to you. The second piece here are the fibers. And these really define the connective tissues. Collagen, elastic, and reticular fibers define the tissues. We're going to talk about the arrangement of collagen. That really tells us what the tissue looks like. And then you learn these, the cells that help us define the tissues. All right. The ground substance, as I said, fluid plus adhesion proteins. And two of them that hold these things together in the matrix are fibronectin and laminin. They serve as the connective tissue glue that allows these cells to connect themselves to the matrix elements. Here's an example that is used. I've seen this on more than one occasion. And I will not use names, but some of you have seen this, where a quote from Colossians is used, and the big golly gee wow moment of the presentation says, Christ holds all things together, and then the religious man then presents this image of the protein laminin and suggests that because it is in the shape of a cross, that somehow this is proof of God's existence within our connective tissues. Now, I saw a few smiles across the room already, and that encourages me because you're already educated enough to see the fallacy in trying to prove God this way. This is not a scientific way of proving God's existence. In fact, these are scanning electron micrographs of laminin. Odd-shaped crosses, don't you think? This is an image of, I took it out. I have on the next picture, I have a picture of fibronectin. It doesn't look anything like a cross. So I do not think in science today that we need to show pictures of molecules that may have a cross shape to them in our effort to demonstrate God's work in creation. You already know some things that can help you with that. Where would you start, for example, if you wanted to demonstrate to a science person that there's a creator?
DNA.
Right. The glycosidic bond on the base has already been widely admitted to in the scientific community. Somebody wrote this language. You don't need to present it this way. These images of things. I mean, we're supposed to spend all our time now looking through the human body for pictures of circular crowns of thorns. And I mean, the insanity of this makes me crazy. So you're being educated. Educate people around you. It's part of your job. Okay, the fibers, as we said, are collagen, elastic, reticular fibers, and I'll point these out to you in the examples as we look at them. The cells, for the third time now, fibroblast, chondroblast, osteoblast, hemocytoblast, hematopoietic stem cells, and then there are other smatterings of cells that we'll see on a couple of these slides. All right, so I want to define connective tissue. All right, let's do it in two. Let's do it two ways. Let's say, let's define epithelium, let's define connective. It's an epithelial tissue. Where is it? Where is it? It's epithelium. Where is it? Where? It's lining, it's covering, right? Anything hollow, what's lining it? Epithelium. Anything covering? Epithelium. All right? So I define epithelium, I think immediately, I think lining covering. Then I think epithelium is defined by its cells. What do you mean by that?
The shape.
The shape of them. Flat, cube, column, one layer, multiple layers. Define it by its cells. I go to connective tissues, and here's how I'm going to define it. I'm going to say if it's a connective tissue, it has these traits. It has cells that produce the matrix of it. If I'm talking about tendons and ligaments and adipose tissue and dermis, and what kind of cells am I talking about? You've got to learn it as we go. What kind of cells am I talking about? Tendons and ligaments and adipose and I'm talking fibroblasts, all right? If I'm talking about nose and ears and knees, I'm talking about chondroblasts. If I'm talking about skeleton, I'm talking about osteoblasts. And if I'm talking about blood, all right, so I've got cells to help me define the tissue. But normally when you look at the tissue, the look of the cell doesn't tell you what it is. What tells you about the tissue and what it is what's between the cells. So what is between the cells? Ground substance, right. And what is in that ground substance? Protein. And what is the major structural protein? It makes up almost a third of the entire body mass. Collagen. Okay, so this is how we think about connective tissues. All right? Here's the first one. This is embryonic mesenchyme. And I am not going to go through and talk about any further details here. I just show it to you. You won't see it again. You won't hear more from me about the mesenchyme. Dr. Moore may have you do a little bit more with this, and I'm not. I want to show you the real-life adult examples. Here's the first one. This is loose or areolar connective tissue. Do you see the cells that you would expect to see in connective tissue proper here? What would they be? It's a connective tissue proper. What kind of cell would I expect to see? Fibroblast cells, okay? So there are fibroblasts in this. Now, does that define what the tissue looks like? No, it's the space between them, right? Between these fibroblasts. And what do I see between them? Collagen, yeah. The arrangement of two of the major fibers are found here, collagen and elastic fibers. We should think in anatomy of collagen as the ropes, and we should think in anatomy of elastin as the rubber bands. In fact, gram for gram, collagen as a living protein is structurally stronger than steel. So to tear a ligament, you have got to put an enormous amount of pressure on that ligament. Gram for gram, stronger than steel. Collagen and elastin define this tissue. Now, where do we find areolar connective tissue? All right. So if I'm doing a dissection on a human, every cadaver dissection begins on the back. So we take the cadavers and we put them face down, and we teach the students how to make cuts on the back to reveal the musculature of the back. When they pull the skin off of the back, they pass through epidermis and dermis and hypodermis. This is going to come to you as we're doing the skin. And then they look at the back, and they're supposed to see, as they look at the back, they're supposed to be able to see this huge muscle extending all the way up the occipital bone and all the way down the back to the 12th thoracic spinous process, the trapezius muscle. And then they're supposed to see this huge muscle wrapping around the sides, extending up to the humerus, called the latissimus dorsi. And the students look at that, and then they look at the atlas. They have a picture in the atlas, and they go, it doesn't look like that. Why does the picture in the atlas look like this in my book? And then I look at the body, and I don't see that. And the answer is because we are packaged. The entire musculature of our bodies is packaged. Now, as we get to the muscles, I'm going to give these some names. This is part of what we call the deep fascia. The fascia, or the packaging of the entire body, is in part, a major part of it is this stuff. So if you cut through it, it would be this. So really, the job of the dissector in learning musculature is to remove enough of the fascia loose areolar connective tissue, to remove enough of it so that the muscle is visible. There's a muscle there, but it's packaged. So this stuff is widely distributed under the epithelia of the body, packaging organs, packaging blood vessels. This is a very important tissue, and it is one of the most abundant of all in terms of location frequency in all the body. Very difficult to go somewhere and not find areolar connective tissue. It's defined by the presence of the proteins, collagen and elastin, and they appear to be in a loose arrangement, hence its name, loose areolar connective tissue. Here's the second one, adipose tissue. Adipose is found under the skin. It's also around the kidneys and eyes and the abdomen and breast. As a postdoctoral fellow at Georgia State, I did a research project in which we, and I won't waste a lot of time here because I know most of you are not interested. I like to bring it up just in case people say, you've got questions, right? So I did this project in which we described the control of 4 different fat pads in hamsters. And humans tend to have adipose tissue that develops in locations. Most of that is under hormonal control. But as it turns out, there's also some nervous system control of this tissue, this adipose tissue, that is different from other connective tissues in the body. So it's very interesting tissue. The first thing you need to know about this stuff is that your book should call it the superficial fascia. So if I say deep fascia to a student, they should think packaging, loose areolar connective tissue. If I say superficial fascia, you should think adipose tissue. So it covers us. It is the fascia that connects the skin to the underlying body. The flesh of you is under your skin, and this is the fascia that helps connect you. So the skin will be defined as outer layer epidermis. We're going to see it in just a minute. I showed it to you once already. Epidermis, stratified squamous. The next layer of skin we're going to call the dermis. Is dermis vascularized? Yes. What kind of tissue is it?
Fibroblast.
It's fibroblast-generated tissue. It's not dense regular. It's dense irregular, right. So as we're working our way down the skin, we have stratified squamous on the outside, dense irregular. This is the third layer in. A lining of adipose under our skin, called the hypodermis, the superficial fascia. Connective tissue, very important. And it is regulated by hormones and nervous system. Very interesting tissue. Okay. Here's the next one of the connective tissue propers. This is says it's loose, but this is what we call reticular connective tissue. And this is the stuff, this reticular connective tissue is what I like to call scaffolding for blood cells. So you're supposed to look at this and see dark lines here that have generated a kind of scaffolding on which cells seem to be, on which these cells seem to be orienting. A scaffolding. Now, if you didn't know anything else about the body, if you've only heard what I've said, what kind of protein do you think reticular connective tissue is?
Collagen.
That's right. Yeah. In fact, there are about 28 different varieties of collagen we know of now. 5 of them are the most abundant 5 in the human body. The first one, type 1, that we find in dense regular stuff, that one makes up more than 90% of all the collagen. But this is a different variety of collagen that makes the reticular connective tissues. You see what I mean by defining everything with the proteins? So the reticular connective tissue is a scaffolding tissue. All right, so let's talk about where this would be found. The first place it says here is lymphoid organs, like lymph nodes and bone marrow and spleen. Okay? So again, you haven't learned this yet. This comes in semester 2. But as we begin to learn the anatomy of structures all over us, one of the things we're going to look at is the inside of a lymph node. And you will see there reticular connective tissue that is supporting the presence of blood cells. And the blood cells I'm going to point out to you there are white blood cells. Everybody knows when you get sick that your lymph nodes tend to swell. The swelling of those tissues is related to the increase in the population of white blood cells that are being produced there to fight some kind of infection. Those cells are being produced on the scaffolding that is called reticular connective tissue. The development of the cells occurs on this scaffolding. Another really important place here is in the bone marrow. Now, test 2 will have this anatomy on it, but any given bone, any given long bone, will have two kinds of marrow in it. In the adult form, our bones have red bone marrow and they have yellow bone marrow. I see some of you mouthing this. The red bone marrow that is in the bones tends to be in the ends of the bones. And it looks like that. Because that's where blood cells are being made. The red blood cells and the white blood cells and the platelets that are being produced in your body are being made in that red bone marrow. And it looks like that. If I showed this to a pathologist, if I showed this picture to a pathologist, they're going to get it immediately. You're looking at bone marrow there. Because if you want to diagnose leukemia, for example, you want a sample of the developing white blood cells that's in the marrow. So you're going to go into the bone and get a sample of the reticular tissue there where the blood cells are developing, and then you're going to look for abnormalities in the development of the leukocytes, the white blood cells. So this is bone marrow. Now, I said there's two kinds of marrow in bone, red and yellow. Yellow bone marrow tends to be in the shafts of the bones. So the red bone marrow is in the ends of the bones, and this is the yellow bone marrow. Your bones, living bones, are a major storehouse for fat. The cavity that is in the shaft of all of our long bones is filled with adipose tissue, yellow bone marrow. So we've talked about bones today, right? Adipose tissue is in the bones. Reticular connective tissue is in the bones. Very important tissues for the human body. Here's the one we've been working our way toward that I keep alluding to. This is dense regular connective tissue. What, in fact, is regular here? Why we call it regular? What? It always the same way. It looks regular, yes? And what is it that is regular?
Direction.
The direction. But what is it that is regular? The arrangement of a protein. You see that? It is a regular arrangement of collagen. This is what tendons, muscle to bone, most ligaments, so joint cavities have some exceptions here. Joint capsules are sometimes dense regular. Tendons, most ligaments, bone to bone, and aponeuroses. Now most people come to me and they know what a tendon is. And they know what a ligament is. Most young people come to me and they've never heard the word aponeurosis. Is that true in this room? Have y'all heard this word, aponeurosis? No? An aponeurosis is a tendon sheet. And we've got them all over us. So the first one that I will point out as we're going through the human body is an aponeurosis on the top of your head. You've been learning the skeleton, right? What is the name of this bone? And what is the name of this bone? There's a muscle, a flat sheet muscle that goes across your frontal bone here. And it has a very unusual name. It's called the frontalis. Isn't that good? Sometimes we make sense, right? Anatomy makes sense. It's the frontal bone, it's the frontalis. There's another muscle on the occipital bone. You want to guess what its name is? Occipitalis. That's the name of it, exactly. So those are flat sheet muscles on the bones for which they are named. If I had a muscle here and it sat on these two bones on top of my head, what would you call those?
Right.
Parietalis. Anybody ever heard of that muscle? It doesn't exist. There is no muscle here. However, this muscle is in fact connected to this one. You see it? They're connected to each other by a tendon sheet. And listen to its name. It is the Gallia aponeurotica. The Gallia aponeurotica. It's an aponeurosis tendon sheet. So we have some others, the abdomen, back. We have some other places where muscles have these sheets for which they attach to their structures, and we call those aponeuroses, dense regular. Next one is dense irregular. Before I go to it, oh, it went. Well, I've already gone to it. Tell me, the outside of my body is covered in epithelium. And it's what kind of tissue?
Simple squamous. Dense regular.
It's not simple squamous. It's stratified squamous. The next layer down would be dermis, and it would be dense irregular. What's the next layer down? Hypodermis. And what kind of tissue is that? Superficial fascia. What is it? Under a microscope, what's it look like?
Oh, it's a.
Adipose. Now I've got the skin off and the superficial fascia off. Am I looking at muscle? Not really. I'm looking at deep fascia. And what kind of tissue is that?
Dense regular.
Loose areolar. Y'all need to put these things together. This has real world context. Yeah? If I'm going to go in a body dissection, what is it? Stratified squamous, dense irregular, adipose, loose areolar, and then muscle.
You say that one more time?
Yeah. Stratified squamous, epidermis, dense irregular, dermis. Help me, what's next?
Hypodermis.
Hypodermis, and that's adipose. Then what? Deep fascia, which is loose areolar. And then what? Muscle. Yeah, these are the tissues that you would encounter if you were going to be interested in what the body is made of. Okay, so dermis of the skin here. Very important example for the dense irregular connective tissue. All right, I made it. When we start next time, 3 kinds of cartilage. And then I will do bone and nervous tissue. And we'll be done on Friday with the tissues. Class, Anatomy and Physiology Exam 1 is getting close. So don't let this stuff get away from you. Okay?